Hello, welcome to Bedroom Builds at the From Python to Rust series, episode 43, type state pattern, continuing from the previous episode where we spoke about the builder pattern. The type state pattern takes advantage of Rust's move semantics and the type system, which allows us to transition between different states at compile time. This in turn gives us the power to enforce certain rules at compile time. So we can require a function to be always called, enforce the order of function calls, forbid the function to be called twice, and mutually exclusive function calls. There's a useful crate available that can generate those needed states automatically, and it's called the typed builder. All right, let's hop over to the code. I reused the user class from the builder pattern episode, but this time the typed builder macro is applied. Its general idea is to provide a nicer object creation syntax. What the typed builder crate allows us to do is the compile time verification that all fields are set before calling the build, compile time verification that no field is set more than once, and if you forget to call a mandatory field, it will show as a deprecation warning in the compile log, which is fairly practical. Let's quickly go over the code. So we can see here we are deriving the typed builder that we have imported first. And we have our user struct with two mandatory fields, the ID and the email, as we had in the builder pattern episode. And now we are using one of the features for the first name. So the builder is applying the default trait implementation for this field. So in this case, for option, it's going to be none. And for the second field, we use more features of the typed builder crate. So again, we use the default implementation, but also we allow the setter to take anything that has the into string implemented, and we are stripping the option, so we do not have to pass a sum when we call the setter. This we can see down here. So first we have our user that creates a builder. Then we set our ID, and here we have to use into to make that string. Then email, again with the into, because we haven't used any of those setter features. Then the first name is using a default, so it would be none if we didn't call it, but here we have to use some string, and then we have to into convert it to be a string object. And the last name you can see is now much easier to use because all we pass is a static string, and the setter feature takes care of wrapping this into a sum and does the into conversion. And at the very end, we call a build, and then we can use the debug output to show the user. Let's show this code in action. So we go to the typed builder example, and we cargo run it. It compiles, and you can see the output is as expected. We actually get the sum builds as the last name, and it's correctly done. Now let's see what happens when we omit the last name, so we don't pass it along. Clear and run it again. And here we can see that the last name is now none because we haven't called it. Now let's see what happens if we omit the email field. So that's one of the mandatory ones. We go up, remove, and run again. And now we can see that we get a compile error. So the build fails because it expected an argument that wasn't supplied. And internally, what they build is now a function that you've called that has been marked deprecated, and that's how you get an actually nicely understandable error message that says missing required field email. That's part of the deprecated associated function, and here you can see this auto-generated super long code. Now, looking at Python, none of those compile time checks are possible, but the transitioning between the states can be emulated at runtime, right? Let's look at our Python code, therefore. So in Python, what I've done is I created a class user that has the static method that returns the user builder. Then we have our normal constructor for setting up all the fields. And for convenience, I implemented the string representation that's similar to deriving from debug. And here we have our user builder, and that's now kind of mimicking what's happening on the automated generated code by the typed builder. It will, if we call ID on it, actually return a class called user builder has an ID with the ID inside. And if you call the email one, it will return a class instance of a user builder that has an email. And then from there, we can now continue. So if we called ID, the only methods that's available is now email, because this class only implements email. So if you were to call ID again, it wouldn't work, because now you have transitioned from the user builder class to the user builder has ID class, and therefore you have changed the type state if you want. And this avoids us calling ID twice, or keeps us from calling methods that cannot be called at the current state. So after you have transitioned into the user builder has an ID state, the only thing that you can call is an email. If you were to construct an invalid user in Python, it would error out at runtime, which kind of emulates the whole concept, but is a much less powerful guarantee, because in Rust we can do it at compile time, so before even running the code. Let's quickly scroll down in this code. Here you can see what happens when we've reached a state where the user builder has an ID and an email. We now can either build out the user already, because we don't care that first and last name, which are optional fields, are none, or we can call those two methods, and they will actually be able to be called multiple times, because what they do is they will just overwrite the first and the last name, and that's fine. And down here we can see that the same code basically as in Rust works. We can call the user builder, then we call ID, email in a chain, and we call build, and in the end we end up with a user. All right, so what really happens on the right side here in Rust with this typed builder, in reality is very, very messy with auto-generated type names, but I can show you on a small graph the basic idea behind it. So what I have tried to implement as a mockup in Python, I have also built as a graph. Let's hop back to our presentation window, go to the next page, and here we can see the graph that is basically built by the typed builder crate. It'll add to our user struct the builder static method, and this will give us a user builder. Now what they do is they have generic type parameters for each of the fields of our struct. So in our case, for the mandatory ones, email and ID, for us to simplify the graph, we start out with having an implementation for no ID and no email. This provides two methods, email and ID, and calling each of them will now transition to the generic parameters changing for the user builder, for example, to have an email defined, and if you called ID, it would have the ID defined, and in there you can then again continue with implementing the corresponding methods that will transition to the next state, which will then be a user builder that has both mandatory fields set, ID and email, and from there you're allowed to call build, or of course first name and last name to set the optional ones. In our example graph, we can also see that we enforce the order of calling the methods, because we cannot call the first name, which is down here, before we haven't reached this valid state of the user builder having an ID and an email. Let's look at the practical manual example that tries to show all the compile time checks that are available to us. For this, I've chosen to make an email builder that helps us construct a valid email according to the RFC 5322. The only obligatory header fields, surprisingly, are date and from. Let's look at the code. So as you can see, we have our struct email and the mandatory fields, the date and the from. Then we have the optional ones. So sender has to be defined. For example, when you have multiple from addresses, you have to declare which one is the sender. Then subject is completely optional. Then we have the carbon copies and the blind carbon copies. And we, of course, have the body of our email. So this we declare ourselves to be mandatory. And for the carbon copy and blind carbon copy, I have decided to use that as an example to have a mutual exclusion. So in our example implementation, you can either have carbon copies or blind carbon copies. This is not following the standard, of course. Then, as we had before in the example, now it's manually implemented. We have the builder static method that doesn't return an email, but an email builder that is starting off with the states no date, no from address, and no carbon copy or blind carbon copy set at all. It's calling the default constructor for our email builder, and then the send method will only dump the object itself onto the terminal. So it's not an actual email sending function for demonstration purposes. Let's hop down to the different states that we are going to implement. So we can see here that we have the state no date, which is an empty struct, and we have the date struct that holds a string. So this is following the new type pattern. And then for our from addresses, we have no from address. We have one from address, which is only a string. And if you have many, of course, we need this to be a vector of strings. So the many from wraps a vector of strings. Same is now true for our mutually exclusive version. We have neither carbon copy nor blind carbon copy. And then we have a vector of strings for carbon copies and blind carbon copies. So first we have to declare our email builder with the generic types D, F, and C. So D is for the date, F is for the from, and C is for the copy variants. And we can see that this is applied to date, the from, and the copies. The rest we can keep because it's an optional setting in our email builder. Continue further down. Now we can see the default constructor does nothing special. It constructs the invalid state for an email builder. It has no date, no from, and no copies. And then we go over the first state. This is our email builder that is implemented for having no date and is generic over F and C. What we can do now is implement the date method that takes anything that implements into a string, and we can see that it returns an email builder that now has transitioned to the next state, which is having a date. So here we have no date and we go to date. And how does this work? Well, we can use the move semantics of Rust. So it takes the email builder, it consumes it, and here we then destructure it. So the itself gets destructured into its fields from sender, copies, and so on. This is then easy to use for constructing it. And these two dots here is we are ignoring the no date field for date that is coming in that we know about because we don't want to use it. We have to set it. So here in our code, we are now setting the date using the new state, which is a date that holds the string. All right, let's continue further down. We can do the same thing for from, but from becomes a bit more tricky because for from, we now have the transition for the email builder. Now it's generic over any D and C, but implemented for having a no from. And if you call the method from, it will transition to the email builder that has one from address. It's the first time that we have called it. So we know that this is the only transition possible, right? We are coming from no from address. We can only pass a thing that implements into string. Therefore, we will end up with 1. Same trick with the destructor, but this time the 2 dots ignore the current from state. And then here we set the from to our 1 from state variant with our new from address. And the tricky part is this: once we have reached this state, we are allowed to call from again. So right down here, we implement now the email builder for, and this is now the tricky part, it's implemented for having a date, 1 from address, and no carbon copies. And this one allows us to call from again. And now we end up with an email builder that has the date set and many from addresses and no copies. Let's look at how we implement the transition from our string to now a vector of strings. Now we can destructure our existing self into all the elements that we need. And here we use the destructure trick that we know that our from is of 1 from, and we want to extract the first from out of this. So in this destructuring, that's what's happening. We now have access to the date, the first from that has been wrapped in the 1 from, and so on. And here now we can create a vector from this. We take our first from that came from self, and then we add the new from that is our argument. Now we end up with a many from that holds the vector of strings. And since we are now in a state that can already also accept carbon copies and blind carbon copies, we implement the carbon copy method as well. This now follows the same trick and pattern that we have already established. This manual implementation of the type state pattern is fairly long, so I've jumped to the first interesting build method that will return us our valid email. It's for the one that has, as you can see here, the date and the many from. Why is the many from more interesting? Well, we have to verify that the sender header has been set as well, because it is obligatory when you have multiple from addresses. We do the destructuring that Rust allows us to have access to the from directly and the date. And here we can now figure out if our sender that was coming in is inside our from list. So here we can iterate over the from list and figure out if any are matching. And if it's not the case, we error out that the sender must be part of the from list. And if we have forgotten to set the sender header, we will also panic out because the sender header is obligatory. So this is now a runtime check, not a compile time check. You can implement the sender method to be checked at compile time once you have reached the many from state. But I've chosen, since we have to do this runtime check anyways, to do both checks as a runtime check. This is, of course, up to the implementer of the API, which one they prefer. Now I've quickly jumped to the carbon copy implementation, which allows also anything that is implementing into string. And the trick that is explained here is Rust allows us to destructure into a mutable declaration of copies. And this allows us then to easily push to the vector the new string. And this allows us then to easily construct the newly list for the email builder state having a longer carbon copy list. And the fairly easy implementation of how we set the subject. So we allow, again, stuff that implements into string. And then we, since it's an option, we simply set the sum variant and we return the email builder, because all we do is overwrite this optional field. Now we're down in the main function of our implementation, where you can see that we are constructing 2 emails. The first one is using multiple from headers and the sender. So for the carbon copy, I only implemented it for 1 from and for carbon copy only, because if you were to manually implement all the variants that now can exist with blind carbon copy, 1 from, many from, this quickly spirals out of control, and therefore you should use macros to generate that code for you. But for demonstration purposes, I implemented this one path on the graph. Let's see what the code does. We run it first. So we can use cargo run, and we can see that we are calling the send method, which uses the debug macro to show us the dump of our emails. So you can see here that we have actually set the 3 from headers that have been given here, that we have the sender header and everything is fine. And down here we can see that we have got our carbon copy vector as well. On the code, we can now play around with this. So if I now omit, for example, the call to sender, then we run into a problem. It will compile, as you can see, but it will not successfully run because the sender header is obligatory. We forgot to set it. Let's make this back into a working state. Let's make one of the mandatory fields a comment. So if we now remove the date call and we run our code, we can see that we are erroring out because we have not transitioned into a state where we can call from again or sender or any other of the methods. So we get this ugly long error message from the compiler, but it avoids us building an invalid email because it simply doesn't compile. Okay, let's get this back into a working state again and try the next thing. So what it shows is we can enforce now that date has to be called at least once at compile time. And now we can also see that we can enforce date being called at max once. So if I now were to copy the date line twice, we will see that it also doesn't compile. Because again, the state that we've reached after we have set the date doesn't allow to set date again. And now to show that we can enforce the order of method calls at compile time is if I now move this from before the date, this means we have not yet reached the state where we have at least one valid from and at least a date. This means I cannot call from a second time because I don't have a valid email yet. So if I now compile this one and try to run it, it will also not work because I cannot call from a second time before I haven't called the date method. Let's put this back into a valid state. So the thing is that I've only implemented CC and not both blind carbon copy and carbon copy to be really in the code. But I have prepared a graph that will show the code that we have almost fully built if you want. And I will explain how we can, at compile time, do a mutual exclusivity check, in this case for either having carbon copies or blind carbon copies. Back to the browser. We now go to our email one. It fits the screen exactly perfect. So at the top, we have our email struct where we implemented the builder. And this is now the simple graph without the carbon copies, just to give you an idea of the compile time checks that I've shown you live on the terminal. So we start with our email builder in no date, no from state. And with the from, we transition to having one from. With the date, we transition to having a date. Calling the respective correct methods again, we now end up with an email builder that has those two set. And from here, we can already start setting subject and body. And of course, we can build out a valid email already. If we, however, call from again, we will now transition to having many froms, which makes the build method verify at runtime if we have set the obligatory sender field. And this also means that this one now allows the additional sender method to be called. Once we have our email, we can call send, and we remember this was just our dump out to the terminal. And now we add the carbon copy and blind carbon copy, which is down here. So now you can see the graph becomes much more crazy. I will have to zoom out. I hope you guys can still read everything. So this kind of gives away the information. We start out again with our email builder. Now we have this implemented for no date, no from end, no BCC. Up until here, we already understood how it works. We have this valid state with at least the date and from set. And from here, we now go off to the many from one that now implements the many from variants of having a carbon copy, blind carbon copy. We can, once we are in the blind carbon copy state, add more blind carbon copies, but we are no longer implementing carbon copies. So once we have reached BCC, we cannot add, therefore mutually exclusive, a carbon copy. Same is true the other way around, right? In the CC1, we only have the CC method implemented. We cannot transition to also having a blind carbon copy. All of these allow us to call the build to get the valid email, which can be sent, and then this is out on the internet. So with all this state mess that gets generated, you can understand now why I said this makes way more sense to use macros to help you out building all of these variants. I hope this was a useful introduction into the builder type state concept. The Rust type system for me is the top reason to use Rust even before the fearless concurrency it provides. This allows us to build APIs that cannot be misused. Even a new colleague could directly be allowed to construct a new email without consulting documentation, because it will simply fail at compile time when he messes up, which either makes him read the documentation or has to hack way too many changes into the code to go unnoticed on a pull request. A great practical example is the Rust embedded programming hardware extraction layer. In order to use a microcontroller's pin for SPI protocol, you have to call the methods that transition the pin on the hardware into SPI state first, before you can even pass it to a device driver constructor. The device driver expects the pin to be in SPI type state, and you cannot cheat that. This means you cannot accidentally run broken code on an embedded device, which is an amazing help avoiding a whole host of errors at compile time, before even copying the binary image onto the small device. Thanks for watching. Coming up next on the From Python to Rust series, I don't really know. If you have suggestions, please let me know in the comments.